Hello everyone, welcome back to Hike. My name is Jasmine Kaur and today we'll be solving a question, search in a row-wise and column-wise sorted matrix. Let's first read the question. I'll be sharing my screen. The question is, given a matrix of size n cross m, where every row and column is sorted in increasing order and a number x, find whether element x is present in the matrix or not. So we are given this example. So here we are given x as 62. We have to search if 62 is present here or not. If 62 is not present in this matrix, so we are returning 0. In this 2D matrix, the special property which it is following is that every row and every column is sorted. Similarly, let's see the next example. So we have this matrix and we have the element 55. So 55 is present in this matrix. So we are returning 1, right? Now let's see how we can solve this. So let's first take a very simple brute force approach and understand it. So in brute force, we don't really have to see any of the properties. We can simply traverse all the elements of this 2D matrix and compare it with the value of x. If x matches any particular element, we'll return 1. If it doesn't match, we'll return 0. So the size of the matrix is n cross m. So this means it has n into m elements. So in the worst case, I need to traverse all of these elements. So it will be the time complexity. The time complexity will be O of nm. And what will be the space complexity? Since we are not using any extra space, the space complexity will be constant or O of 1. Right? Now let's see a better approach. Now what is the special property that this 2D matrix is following? Every row and every column is sorted. Let's take an example. Suppose I have this 2D matrix, 2, 3, 5, 7, say 4, 5, 7, 8. Then you have, let's say, 6, 9, 10, and 11. Right? Now, every row and every column you can see here is sorted. It's not like that you have one row and then the next row is sorted. So 4 is not greater than 7. 6 is not greater than 8. But here every row is individually sorted and every column, it is individually sorted. Right? So now a better approach could be, we know whenever an array is sorted, we can directly apply binary search here. So what I can do is, first I can try finding out the value x in row number 0. So I can use binary search in row number 0. Then binary search in row number 1, then binary search in row number 2, because individually all these rows are sorted, right? So I can apply binary search on every single row, right? So let's say it has n rows, because it's an n cross m matrix, right? So every row has m elements. So if I apply binary search on an array of size m, what is the time complexity? The time complexity will be log of m. Now, how many times I'm applying this binary search? I'm applying this binary search n times because there are n rows. So the time complexity of this approach will be O of log n log m. Is it clear? So log n is the time complexity of finding out the value x in a particular row because it contains m elements. Now I'm applying this binary search on every row that there are n rows. So n into log m, the total time complexity will be O of n log m. And what will be the space complexity? I'm not using any extra space. So the space complexity will be O of 1. Clear? Now let us see an optimal approach. Let's take the array once again. We have 2, 3, 5, 7, 5, 7, 4, 5, 7, 8, 6, 9, 10, and 11. So now let's observe each of the 4 corners. So let's see, I'm at 2. Okay. So if I go towards right of 2, all the elements are greater than 2. So the elements here are increased. And if I go down from 2, The elements are again increasing because the columns are also sorted. So from 2, if I go in either directions, you can see the elements are increasing. Similarly, let's see 11. If I go up from 11, all the numbers are smaller than 11, so they are in decreasing order. And if I go towards left of 11, again all the numbers are smaller than 11. This is also in decreasing order, right? Now let's observe these two corners, 6 and 7. Let's observe them. If I go to 7, if I go towards left of 7, the numbers are smaller than 7. So these are in decreasing order. But if I go towards down direction, the numbers are more than 7. So this is in increasing order. Similarly, if you see 6, if I go up from 6, the numbers are smaller. So this is decreasing. But if I go towards right of 6, the numbers are increasing, right? So if I take 7 or 6, that means the top right corner or the bottom left corner, I can move in two directions, and in each of these two directions, the numbers will be different. On one direction, I'll get smaller numbers. On the other direction, I'll get larger numbers. So if I want to search for an element and I'm present at this index, I know if I want to find out the larger element, I have to go in some particular direction. And if I want to find out the smaller element, I have to go in a different direction, right? Because the numbers are in decreasing order in one direction and increasing order in the other direction. Clear? So let's see, in this particular array, I want to search for an element 4. And I'm starting from top right corner. I'm starting from top right corner and I want to search for element 4. Now, how will you do this? I'm at position 7. So I'm at 7. So I'm at row number 0 and column number 3, right? And the element present at 0, 3 is 7. So this is greater than x. I want to find out a number which is smaller than 7, right? So if I go down, I'll get greater numbers. So I have to go left. That means in this particular column of column 3, I will not find the number which is smaller than 7. So what I can do is I can discard this particular column. So what I can write is I can write column minus minus and I'll go to column number 2. This means I have discarded this particular column, right? Now I am at this position. So I am at 5. Row is again 0 and now column has become 2. Now if I see the element present at 0, 2, I'll see the element is 5. Again, this is greater than x because x is 4. Now again, that means I do not want to go down because then I'll find larger numbers. I'll have to go towards left. So I can again discard this particular column as well. So I'll again write column minus minus. And now I'll go to column number 1. Row is still 0 and column is 1. Now if I want to find out what's the element present at 0, 1, what is the element? It is 3. Now 3 is smaller than the number I want to find. Now since 3 is smaller, I need not go left. This means I'm not discarding this column. I want to go down because if I go down, the numbers will be in increasing order. So I'll discard this particular row now. So I'm discarding this row and moving down. So here I'll write row plus plus. Now the row value will become 1, right? So now I'm at row 1, column 1. So what is the element present at row 1, column 1? So if I write array of 1, 1, the element is, you can see here in 1, 1, the element is 5. Now 5 again is greater than x. I want to decrease the value. So if I go down from 5, I'll get greater numbers. And if I go left from 5, I'll get smaller numbers. So I'll have to discard this particular column and go left. So I'll again do column minus minus. So now I'll reach column 0. So now I'm at row 1 and column 0. So if I search for the element 1 comma 0, what is the element present at 1 comma 0? It is 4. So this is equal to the element we want to find out. This is equal to x. So this means the element 4 is present in this particular matrix and we'll return true here. Now suppose by discarding rows and column, we go towards a row number which doesn't exist or a column number which doesn't exist. We'll simply return 4. Here we are starting from row number 0. So row can go up to n and we are starting from column m minus 1. So column can go up to greater than equal to 0. So if any of these two conditions fail this and we are not able to find out the element till then, this means that the element is not present. Now, what is the time complexity of this approach? So you can see in this particular approach at one iteration, I'm either discarding a particular row or I'm discarding a particular column. So in the worst case, I'll have to discard every row and every column, right? Now in this particular scenario, when I'll have to discard every row and every column, so the time complexity will be O of n plus m. Or whenever you have a plus sign, you can write it as max of n comma n, right? So the time complexity can also be written like, and what's the space complexity? We are not using any auxiliary space. So the space complexity will be O of 1. And this is the time complexity. Is it clear? So let's try to code it now. So here we have a vector of integer. The name is matrix. We have n as the number of rows and m as the number of columns and x is the element we want to search. So we'll start from the top right element. You can also start from the bottom left element, but here we are starting from top right element, right? So the element from where I am starting is, so the row number of that particular element is 0. And the column number of that particular element will be m minus 1. And I want to continue doing this while my row number is less than n as well as the column number is greater than equal to 0, right? Now I'll check if this particular element, if matrix of r comma c, if it is equal to the element I want to find out x, in this case we'll return true. Else if the element present here at index R and C is smaller than X. So this means I'll have to increase my value. That means I want to go to the rows which are down to it. So I'll have to discard this particular row. So here I'll do row plus plus and otherwise I'll do column minus minus. Right? And in the end, when this while loop breaks, that means I'm out of the matrix and still the element is not found. In this particular scenario, we'll return false. Let's run the code. Okay, and let's try to submit this. So all the test cases are passed. So all the test cases have passed. If you have any doubts, just write it down in the comments below and I'll be more than happy to solve. Thank you.